This video is going to discuss how we calculate the probability of compound events. So, what is a compound event? Well, compound events are events with more than one outcome. Some compound events are based on a bunch of simple events. We have done some of those. For example, the probability you roll a single die and you roll an even number. That is a compound event because it includes rolling a 2, a 4, and a 6. So 3 different outcomes. In this case, we're going to step it up a notch, and we're going to talk about compound events that have more than one outcome, and that we also have to think of some other things that have to take place at the same time. And let me describe what I mean by that. So suppose you grab 4 M&Ms from a dish at random. Describe the color of M&Ms you grabbed if, at most, 2 of the M&Ms are yellow. Okay, well, first of all, let's think about what it means to say at most 2 are yellow. One of the things that does mean is that 2 of them M&Ms could actually be yellow. That's true. But if we stop there, that is saying exactly 2 of the 4 M&Ms are yellow. And that is not what this phrase at most means. At most is talking about a maximum of 2 being yellow. So that means I could have 2 M&Ms that are yellow, or I could have 1 M&M that's yellow, or I could have no M&Ms that are yellow, and I could have some other colors. Now, specifically, I don't know what the other colors of M&Ms would happen to be. And honestly, it doesn't matter because all we're looking at are M&Ms that are at most yellow. So what I need to emphasize here is that if you have 2 yellow, you have 2 other M&Ms that aren't yellow. If you have 1 yellow M&M, you have 3 others that aren't yellow. Or maybe you don't have any yellow M&Ms and then you have 4 that aren't yellow. Now, the dots there don't mean they're purple, okay? The purple dots could represent anything. It could be that you have a blue and a green, a blue, a green, and a red, maybe 2 greens and a blue and a yellow or an orange. It doesn't matter. It's just the point being it's not a yellow, okay? So let's take another example. Here it says at least 3 are blue, okay? At least 3. So that does include 3 of them could be blue, but at least 3 does not mean exactly 3. At least means a minimum. So if I have 4 candies, that could mean 3 of them are blue, or it could mean all 4 of my candies are blue, and that would satisfy the at least 3 blue. The other part, however, that has to come into play is that if 3 of them are blue, I need a 4th M&M that is not a blue M&M. And similarly, if we look at this next scenario, no more than 1 is green. No more than 1. So that means I can't be any bigger than 1. No more than 1 green means I might have 1 green, or I might not have any greens. So again, the phrase no more than 1, that's talking about a maximum. And so again, using my purple dots to signify the other M&Ms, if I have 1 green, I have 3 that aren't. Or if I don't have any greens in my hand, I have 4 M&Ms that aren't green. Those are the kind of things we're going to need to think about when we do the compound event probability in this particular lesson. So let's take a look at an example about a 5-card hand. Okay, so we're going to be dealt 5 cards from a standard deck. What is the probability we are dealt at most 1 face card? At most 1 face card. So again, looking at that phrase, at most 1, that means I could have 1 face card, or I might not have any face cards. So one face card or no face cards, because at most one, again, is a maximum. Well, then I have other cards to take into account. In the case of me having one face card, then I must have 4 other cards in my hand that are not face cards, what my NF stands for. Or if I don't have any face cards in my hands, then what I have is I have 5 cards in my hand. All of them are not face cards. Now I want you to keep that little visual there in mind as we start calculating this probability. So now let's go back and start tying a bunch of things together. Whenever we are being dealt cards, there is no repetition. We're not being dealt the same card twice, okay? And order doesn't matter. So when it comes to calculating this probability, we will be using combinations. Now, when we build our combinations, we're going to keep in mind exactly what we did right here. One face card and 4 cards that are not face cards, or 5 cards that are not face cards. Now let's think about building our combinations. So when we have one face card, think about how many face cards there are in a deck. There are 12 face cards. We are going to choose one of them to be in our hand. And we need 4 cards that are not face cards. So if 12 cards in the deck are face cards, there are 40 cards that are not, and we are being dealt 4 cards that are not face cards. Okay, and notice we want one face card and 4 non-face cards, the and represented by a multiplication symbol. Okay, or here's where our plus comes in, here's our or. We want 5 cards that are not face cards. So again, there are 40 cards in the deck that are not face cards. We would be dealt all 5 of them. This is going to be divided by the total number of ways we can be dealt any 5 cards from a deck. There are 52 cards in a deck. We would be dealt 5 of those. Calculating this, we will end up with 12 choose 1 times 40 choose 4. That number is 1,096,680 plus 40 choose 5, which is 658,008 over 2,598,960, and adding those two numbers together in the numerator, we will get 1,754,688 over 2,598,960. That is the probability we would be dealt at most one face card. Again, no need to reduce at all. So let's take a look at another example. Let's say this time we have 3 blue, 4 red, and 7 green paper clips in a little dish. We're going to grab 4 at random. What is the probability at least 3 of them are green? Okay, at least 3 are green. So at least means we're talking about a minimum. So I'm grabbing 4 paper clips. That means I will end up with 3 that are green, or possibly all 4 are green. In the event 3 of them are green, 1 of them would not be green. I don't know if it's red or blue, and it doesn't matter. I just know it's not a green paper clip. Okay, so whenever it comes to calculating this, again, No repetition. We're not pulling the same paper clip out over and over again, and order doesn't matter. So when I'm doing 3 green, we need to think there are 7 green paper clips. I'm going to choose 3 of them. And I need 1 paper clip that is not green. Now, whenever we look at our paper clips that are not green, that's the 3 blue and the 4 red. And we don't care if they're blue or red, we just know they're not green. So that is 7 total paper clips that are not green. So we're going to use that here. 7, choose 1 that is not green. Or, there's our or right there, maybe we end up with 4 green paper clips. So that would be 7 green paper clips, choose 4. Our denominator is therefore going to talk about the ways we can get any 4 paper clips from all of the paper clips that are in the group. So whenever we look at how many paper clips there are total, there are 14 total paper clips. We are picking up 4 of them. Again, doing a calculation, 7 choose 3 times 7 choose 1 is 245. 7 choose 4 is 35. And 14 choose 4 is 1001. Adding our 245 and our 35 together, we find out the probability of getting at least 3 green paper clips is 280 over 1001. All right, let's practice one more example. We're going to return to our deck of cards. Again, being dealt 5 cards from a deck. What is the probability we are dealt no more than 2 diamonds? No more than 2 diamonds. No more than is talking about a maximum. So if we have a maximum of 2 diamonds, that means we could have 2 diamonds, or we could have 1 diamond, or we could have no diamonds in our hand. Okay. Now, what are the other cards? Because remember, we need 5 cards in our hand. We don't just have 2 diamonds and then nothing else. There's 2 diamonds and there's 3 cards that are not going to be diamonds. So I'm going to put in ND for not a diamond, not a diamond, not a diamond. If I have 1 diamond, I would have 4 cards that are not diamonds. Or if I don't have any diamonds at all, I have 5 cards in my hand that are not diamonds. So now let's calculate those probabilities. Okay, starting with I have 2 diamonds. So in a deck, there are 13 diamonds. I have 2 in my hand. And along with those 2 diamonds, I would have 3 cards that are not diamonds. So in a deck, there are 52 cards. If 13 are diamonds, 52 minus 13 of them, or 39 of them, are not diamonds, and I would have 3 not diamonds in my hand. Or maybe I have 1 diamond in my hand. So again, in the deck, there are 13 diamonds altogether. I have 1 in my hand, and along with that, I would have 4 cards that are not diamonds. So 39 cards that are not diamonds, I would be choosing 4 of them. Or maybe I don't have any diamonds in my hand, and what I have is 5 cards that are not diamonds. So out of the 39 cards that are not diamonds, I would have 5 of those in my hand. And again, the denominator is the total number of ways I can have any 5 cards dealt to me. So 52, choose 5. So again, doing the multiplication, 13 choose 2 times 39 choose 3, excuse me, is 712,842 plus 13 choose 1 times 39 choose 4 is 1,069,263, and 39 choose 5 is 575,757. How's that for a fun number? My denominator is 2,598,960. And so again, adding up those numbers in the numerator, we come up with a total, oop, that did not work. I hit a multiplication button just instead of an addition. That didn't work out very well. 10692. Oh, that's better. Okay. We end up with 2,357,862 ways that we could be dealt no more than 2 diamonds out of the 2,598,960 different 5-card hands. So I would say your chances are pretty good that you're dealt no more than 2 diamonds, wouldn't you? All right, so now be applying those rules. And the one thing I'm really going to remind you of is that anytime you are building out your, in this case, 5-card hand, make sure you do account for all 5 cards. Don't just stop at 2 diamonds, okay? Don't stop at 2 diamonds and not think about the 1 diamond or the no diamond scenario. And again, make sure in every instance you have accounted for the total number of items that you are choosing. And then the and is a multiply and the or is an add. That theme has carried through all of our probability problems, and it continues through these as well.